Hi, I'm Jim Burnham. Welcome to Chemistry. Today we're talking about chemical quantities. Remember in chapter 5 we talked about atoms as the fundamental building blocks of the material world. And then in chapter 6 we talked about the rules for naming those fundamental building blocks and chemical formulas. And today we're going to talk about how to count those fundamental building blocks. And because they're so small, we're going to use a special way of counting small objects. That's known as the mole. The mole is a measurement of how much of something. How do we count many things? If we have a lot of things to count, we come up with different clumps. So if it's a pair, it's 2. If it's a dozen, 12. How many is in a baker's dozen? 13. How many is in a gross? Well, you may not know this one. 144. How many is in a ream? If you work in a paper store, you'll know it's 500. But how about something really, really large? How about counting grains of sand, for example? Is it practical to count each and every individual grain? Well, of course not. So how else could we do it? How could we measure or quantify the grains of sand? Well, you might think we could weigh. We could take a certain amount and weigh it. Say, listen, let's take 10,000 grains of sand and weigh it. And if that turns out to be some usable amount, then every time we have that amount, we have 10,000 grains. Or maybe we take a certain volume of the sand. Maybe we take a quart of sand or a gallon of sand. We painstakingly count every grain in a gallon, and then we know however many numbers of gallons we have, that's the number of particles we have per gallon. Let's look at something simple like an apple. We can measure apples in 3 different ways. So at a fruit stand, for example, they might be sold by the count, say 5 apples for $2. Or at Ralph's, a grocery store, they might be sold by weight, say 89 cents a pound. At an orchard, they might be sold by volume, say $9 a bushel. Okay, all of these, by count, by mass, or by volume, can be equated to a dozen apples. So look at this. By count, we can say a dozen apples equals 12 individual apples. Or by mass, we could say a dozen apples equals, say, approximately 2 kilograms. Or we could do it by volume. A dozen apples equals, say, 2/10 of a bushel of apples. And now we can convert between these units by using their relationship to a dozen apples. We could calculate the mass, for example, of a bushel of apples, or the mass of, say, 90 apples. So how would we do that? How would we calculate the mass of 90 apples? Well, we'd use these conversion factors. In every dozen apples, we have 12 individual count apples. And in every dozen apples, we have, say, approximately 2 kilograms. So we would set it up. Say we start with 90 apples, and then we set up our first conversion factor, a dozen per 12 apples. That converts it to a dozen. And then we convert it with another conversion factor, 2 kilograms per dozen. We see that we cancel out apples, we cancel out dozen, and we convert it to weight. In this case, it turns out to be about 15 kilograms of apples. Now, how can we apply something similar to the idea of counting atoms and molecules? How are we going to count these guys? This takes us to one of the most important concepts in chemistry, and that is known as the mole. You have got to understand this concept if you want to make any progress in chemistry. The mole is the SI, the metric system unit, for measuring the amount of a substance. Well, all right, that in itself may not tell us very much. Remember, there are 7 SI base units, right? We measure time in seconds, length in meters, mass in kilograms, current in amperes, Kelvin, temperature, luminosity in candela, and amount in moles. Okay, well, what is a mole? Well, it's not this cute little guy. It's not this not so cute little guy. There's a clip from one of my favorite movies.
Jolly good work.
Yes, nice to mole you. Meet you. Nice to meet you, mole. Don't say mole. I said mole.
Stop!
Bye, mole. Mole. Mole.
Oh, shut up!
Mole, 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 mole.
So counting really, really large quantities. How would we count, for example, a giant jar of jelly beans, say at the state fair? Guess how many jelly beans are in this giant jar? All right. Again, we might think we could, estimate the volume, but here's a principle I like to use. WWCD, what would criminals do? So let's say you had a big load of drugs that you were going to sell, and you want to get paid in $100 bills. You want to get paid in cash. And the deal goes down in some dark warehouse, and you got to make it fast, or you're going to get caught. You can't bring a bank teller down there to verify the money. You can't bring a money counter. So how can you verify the number of dollar bills that you need for your drugs? Well, drug dealers, they weigh the cash. They count it by weighing it, which is much faster than counting it in individual bills. It turns out that $100 bills, if you want $1 million in $100 bills, it's exactly 22 pounds. So if you get a suitcase and you subtract out the weight of the suitcase and the net weight is 22 pounds of hundreds, that's $1 million. So you're welcome very much. Now, atoms and molecules are incredibly small. So small, they're inconceivably small. And yes, that's going to take me to this clip from another of my favorite movies.
Inconceivable!
You keep using the word. I don't think it means what you think it means.
But we can still count these inconceivably small atoms and molecules. They're so small we can't even see them, not even with the best microscopes. We can still count them by weighing them, just like the criminals do. How many molecules of water would you guess are in 1 ounce or 18 grams of water? Do you think there are hundreds of molecules? Maybe you guess there's thousands. Maybe you guess there's millions. That seems like a pretty good guess. I mean, gee whiz, it's just a tiny little ounce of water. How many little particles of H2O could there be in there? Billions? More. Trillions? More. Quadrillions? Certainly. That's got to be it. No. Quintillions? No. Hextillions. Yes, there are 602 hextillion molecules in every ounce or 18 grams of water. This is how it's written out, right? 20, 2, 4, 6, what do we got? 3, 6, 9, 12, 15, 18, 21. So 602 followed by 21 zeros. It's an astonishingly large number. In scientific notation, we would write this as 6.02 times 10 to the 23rd. Remember this number. This number is known as a mole. It's also known as Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd. So a mole is an Avogadro's number of something. If you have an Avogadro's number of something, you have a mole of something. This means we can count the number of water molecules based on weight. Now, how big a number is that? Well, if you had a mole, an Avogadro's number of animal moles, it would cover the entire Earth with a layer more than 8 million animal moles thick. If you line them up end to end, a mole of animal moles, an Avogadro's number of animal moles, would stretch from Earth to the nearest star, Alpha Centauri, which is 4 light years away. That's as far as light can travel. And light travels 186,000 miles per second. So more than 2 million times. So it would stretch back and forth between us and Alpha Centauri 2 million times. A mole of moles. That's astonishing. It's an astonishing large number. Now, Why that particular number? Well, we need a number unit that gives us a usable amount of atoms or molecules. As we saw, a mole of water, an Avogadro's number of water, is an ounce of water. That's a usable amount of water. I can weigh that, and I can use that in a test tube for a chemical experiment. That particular number, Avogadro's number, 6.02 times 10 to the 23, it's the number of atoms equal to, dun, 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 the atom's atomic mass number converted to grams. What is atomic mass? Well, remember, let's go back to the periodic table. In the periodic table, right, we have the number, the proton number, so that's its atomic number. But we also have its atomic mass expressed in AMUs. So this is the atomic mass of hydrogen, just over 1. This is the atomic mass of boron, 10.8. This is the atomic mass of carbon, 12. And this is because, as we'll see, so carbon, atomic mass, 12. This is because carbon is built out of 6 protons and 6 neutrons, and so that's basically the weight of carbon, 12, the weight of the protons and neutrons. So that's we count that in atomic mass units. That's the weight of neutrons and protons. So now we're saying let's pick an amount of carbon that weighs the same as its atomic mass of 12 in AMUs. Let's get enough of those to give us the same number, 12, in grams. So that the number of atoms that makes up 12 grams of carbon-12, so the number of atoms that makes up this much weight of carbon-12 turns out to be the mole. That's why we picked the mole. The mole converts atomic mass in AMUs to grams, and that's a usable amount. Again, 602 hextillion. That's how many atoms of carbon you need to give you 12 grams of carbon. It's a lot. So a mole is 6.02 times 10 to the 23 of anything. And here's the magic. The mole converts atomic mass on the periodic table to grams I can use in the lab. I can count them in the lab. I can calculate them. I can do something with them. So that's the magic of the mole. It takes the number on the periodic table of atomic mass and converts it to grams in the laboratory. What's the practical payoff? Well, let's say I want to make something out of chemicals. Let's say I want to make salt. Okay, well, I look it up and it's a synthesis reaction. I have to combine chlorine gas and sodium metal, and it combusts to make NaCl. And here's the balanced chemical reaction. I'm going to need 2 parts sodium to 1 part chlorine, the diatomic molecule, and that will make 2 parts NaCl. So here's my chemical recipe, right? But can I get just 2 atoms of sodium and react them with 1 diatomic molecule of chlorine to produce 2 NaCl? No. I mean, I can't work with something that small. I mean, so, but I know I need sodium to chlorine in this 2-to-1 ratio. So how much sodium do I need to completely react with the chlorine? As I said, can't use individual atoms. They're too small. Like these kittens are too small to live in this cup. They're too small. But I can count out equal numbers of atoms or molecules by weighing out equal numbers of moles. You see, if I have 1 mole of sodium and 1 mole of chlorine, then they each have the same number, right? An Avogadro's number of each. So I can weigh out a mole of sodium, and I can weigh out a mole of chlorine, and then I can combine them to make salt. So how much is a mole of sodium? Well, remember the mole converts atomic mass to grams. So a mole of sodium is 23 grams. A mole of chlorine, the diatomic molecule, 2 chlorines, is going to be double. It's going to be 2 of 35.5, so 70.9. So now I know that if I have a 2-to-1 ratio, I need 2 moles of sodium. I can combine that with 1 mole of chlorine, and that will create 2 moles of NaCl. So how do I get 2 moles of sodium? I get 46 grams of sodium. How do I get a mole of Cl2? I get 70.9 grams of chlorine, and that will make 116.9 grams of salt. And notice this preserves my conservation of matter, right? The principle that matter can be neither created nor destroyed. The amount of reactants that I have equals the amount of product that I have. So now I have a chemical recipe. So bottom line, a mole is a chemist's dozen, right? Some things we count by dozen, paper we count by reams. Well, molecules we're going to count by Avogadro's number, 6.02 times 10 to the 23rd. We're going to count by moles. This helps me make and calculate chemical recipes. Except by dozen here in chemistry, I don't mean 12, I mean an Avogadro's number, a giant D number, 6.02 times 10 to the 23rd. This gives me a usable amount of something. That something is going to be equal to its atomic mass in grams. Remember, the mole converts atomic weight to grams in the laboratory. This allows chemists to calculate and react large numbers, inconceivably large numbers of atoms or molecules based on practical lab-appropriate weights. Okay, now we need to introduce a new term, representative particle. This refers to the species that's present in the substance. Whether we're considering atoms or molecules or formula units, we want to say, oh, when we're talking about atoms, what's the representative particle? When we're talking about molecules, what's the representative particle or unit that we're going to count molecules in? And when we talk about ionic compounds or ions, what is the representative unit or particle that we're going to count them in? Okay, so let's consider them in turn. For most elements, the representative particle, the thing we count when we're talking about atoms, is the individual atom. So I'm talking about sodium, I'm going to talk about atoms of sodium. I talk about silicon, I'm going to be talking about atoms of silicon. Helium is composed of helium atoms, so that's what we'll count. Iron is composed of iron atoms, so that's what we'll count. So it seems like we could just say, well, we'll count all elements in terms of their atoms, except there's a tiny complication. 7 elements don't exist as monoatomic, as single atoms. They exist in pairs, known as diatomic molecules. So here are the 7 diatomics that we need to learn: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These 7 exist as diatomic molecules. So you're never just, if you're just going to add oxygen to something, let's say you're going to combust something, burn something with oxygen, you're never going to add just a single atom of oxygen, because oxygen comes as a pair. So same thing, hydrogen comes as a pair. So anytime you react any of these things, remember when I was reacting with sodium and chlorine, why do you think I use chlorine as a doubled up? Right? Because that's how chlorine comes. Chlorine in the wild comes as Cl2, a diatomic molecule. So that's how we're going to count it, and that's how we're going to calculate its molar mass. So the way to remember your 7, you can use Brinkelhoff, which is what I learned years and years ago, or you can use this mnemonic: have no fear of ice cold beer. Have no fear of ice cold beer. Hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, bromine. Now, when we look at molecular compounds, the representative particle of both the diatomic molecules and all other molecules is going to be the molecule. That's the thing we're going to count, the whole molecule. So if we're counting water, we're going to count the H2O molecule. How about ionic compounds? What's the representative particle, the unit that we're going to count in when it comes to ionic compounds? Well, it's the formula unit, right? The lowest whole number ratio of your positive and negative ions that balance each other out. So here are examples of representative particles. Okay, if we're talking about iron, we're going to count it in atoms. If we're talking about atomic, an atom of nitrogen, right, then we're going to be just a single N. But if we're talking about nitrogen gas as it lives in the real world, that's going to be a diatomic molecule, and so we're going to count that as an N2. Okay, so notice we count atomic nitrogen and nitrogen gas differently, because one is just the single atom and the other is the diatomic molecule. Water we count as a molecule. Calcium we count as an ion. Calcium fluoride, an ionic compound, we count as a formula unit, CaF2. Glucose, big fat starch, we count as a whole molecule. Okay, so you get the idea. Particles are counted in moles. So we're going to use the type of representative particles and get moles of each. So we can talk about moles of atoms, moles of molecules, moles of formula units. So if we take the atomic mass of carbon, which is 12, and we take a mole of them, an Avogadro's number of them, it will weigh 12 grams. Remember, the mole converts atomic mass to grams in the laboratory. Likewise, if we have a mole of copper, right, its atomic mass is 63.5, then that mole will weigh 63.5 grams. So the amount of something, a mole, is equal to its atomic mass in grams. That's what a mole is. The amount of something that converts atomic weight to gram weight. So we can call this gram atomic mass if it refers to an atom. Remember, atomic masses are the weighted average of all the isotopes. So the average carbon atom weighs 12 AMU, and you can see that's 12 times heavier than the average hydrogen atom, which weighs 1 AMU. So if you took 100 carbon atoms, right, they would still be 12 times heavier than 100 hydrogen atoms, right? Because 100 times 12 AMUs, 1200 AMUs, is going to be 12 times as much as 100 times 100 AMUs. So any number of carbon atoms is always going to be 12 times heavier than the same number of hydrogen atoms. Therefore, 12 grams of carbon and 1 gram of hydrogen, that preserves that 12 to 1 ratio. They contain the same number of atoms, namely an Avogadro's number of them. How many atoms are contained in the gram atomic mass of any element? An Avogadro's number. So 12 grams is the gram atomic mass of carbon 12. Therefore, 12 grams equals a mole of carbon 12. And 1 gram, that's equal to its atomic mass of 1, is equal to a mole of hydrogen. And 24.3 grams of magnesium, which is the gram atomic mass of magnesium, equals a mole of magnesium. So we can have moles of anything, not just atoms. We can have moles of atoms, we can have moles of molecules, moles of ions, moles of formula units, moles of anything. But when it comes to molecules, we just have to find the mass of the molecule in grams, which we take from the atomic mass for each element in the compound. So let's say, what is the mass of a mole of this molecule, H2O? Well, it's going to be equal to 2 H's, the mass of 2 H moles, plus the mass of 1 oxygen mole. So we know that a mole of oxygen weighs 16 grams, that's equal to its atomic mass in grams, And a hydrogen mole weighs 1 gram each, so 2 of them is 2 grams. So again, we take the atomic mass, right? We convert it to grams. That's what a mole does. And then we just add them together. 16 grams for the oxygen mole, and 2 grams for a mole each of hydrogen, 2 moles of hydrogen. That gives us 18 grams. So a mole of water would weigh 18 grams. This is called the gram molecular mass. The mass of a mole of molecules. So the mass of a mole of molecules in grams. So we can say a mole of H2O equals 18 grams of water. Conversely, if I have 18 grams of water, I have an Avogadro's number of water molecules. So now we can convert between weight and number of molecules. So if I had 36 grams of water, how many molecules would I have in 36 grams? Well, I know that if I have 18 grams, I have a mole. So 36 is twice as many, so I must have 2 moles, right? So I can convert from grams, if I know the mass of a mole, to moles. So 18 grams of water gives me a mole of water. And then I can convert from a mole using Avogadro's number. If I have 1 mole of water, I multiply it by Avogadro's number, 6.02 times 10 to the 23rd, and that gives me the number of water molecules. Can we have moles of ionic compounds? Of course. But again, since our representative particle of an ionic compound is the formula unit, not the molecule, we have another term we use, this gram formula mass. It's the mass of a mole of the unit formula in grams. And we find it the same way as we find molecular mass. We add up the individual atomic masses of the ions in the formula unit. So what is the gram formula mass of calcium iodide? Well, we're going to add up a mole of calcium and 2 moles of iodine. So we look at our chart and we say, oh, calcium is 40.1 per mole and iodine is 126.9. There's 2 of them. We add them together. We have 293.9 grams for this formula unit. And that many grams of a formula unit is equal to a mole of this formula unit. So the key concept is that moles allow us to count inconceivably large numbers of things like atoms and molecules and formula units by weighing them. A mole of any atom or molecule or ion is a quantity that converts its atomic mass to grams. So here is a mole of several different substances. Here's a mole of lead. An Avogadro's number of lead, 6.02 times 10 to the 23rd. A mole of copper. An Avogadro's number of salt. An Avogadro's number of potassium dichromate. An Avogadro's number of mercury, water, sulfur, and so on. Okay, and you're going to see that they weigh different things because they're made up of different weighing atoms. And so a mole of each of the particular atoms is going to vary depending on how many are clustered together in the molecule. But all of these, whatever their size, whatever their different weights, all have the same number of atoms or molecules or formula units, namely Avogadro's number. So we've also learned 3 important related terms. Okay, gram atomic mass, that's a mole of atoms. Gram molecular mass, that's a mole of molecules. Gram formula mass, that's a mole of formula units. And all of them give us a mole of the representative particle. So all of them, these equal a mole. So if I have an Avogadro's number of any of those things, I have a mole of the representative particle. So let's just invent a term or use a term that encompasses all 3 of those previous terms. And that's going to be this term, molar mass. So we're going to forget about these 3 terms, gram atomic mass, gram molecular mass, gram formula mass. We're just going to say molar mass, the mass of a mole of whatever representative unit we're talking about. So the molar mass is the mass in grams of 1 mole of whatever substance we're talking about. whether it's individual atoms, molecules, or formula units. So put on your thinking cap. In your own words, what is a mole? Hopefully you will say something like the amount of a substance that contains an Avogadro's number of representative particles of that substance. What is the molar mass of any substance? Well, it's the mass in grams of 1 mole of the substance, whatever we're talking about. Atoms, molecules, formula units. Okay, could we use moles to count anything, or is it reserved just for atoms and molecules? Well, as I already alluded to, you can count anything. You can count animal moles or crocodiles or stars or whatever you want. You can count anything in moles. But it's particularly useful for counting atoms and molecules and formula units because they are so very, very tiny. And you have so very, very many. You have hextillions of them in a very, very small container. 1 ounce has 602 hextillion water molecules. Could we define the mole in terms of ounces or pounds instead of grams? I mean, could we pick another number that converted atomic mass on the periodic table to ounces instead of grams or pounds instead of grams? Yeah, we could have picked another number. It would be a different number. It might be quite a bit larger. It might be 10 to the 24, 10 to the 26 or something. But we could pick another number that would convert atomic mass on the periodic table to ounces, 1 ounce or 1 pound or whatever unit that we're looking for. We happen to go with grams because we're using the metric system. And that's what the mole does. The mole converts from atomic mass on the periodic table to grams, usable grams in the laboratory. What practical difference would that make? It would be a different number. Instead of Avogadro's number, it would be some other number. It would be some other gianty number that converted atomic mass to ounces or atomic mass to pounds. So, review of the key concepts. The mole is the SI unit for amount of substance. And a mole of any substance, atoms, molecules, formula units, alligators, pennies, is 6.02 times 10 to the 23 of whatever representative particles we're counting. For most elements, the representative particle is the atom. Except for the diatomic molecules, the 7 of those have no fear of ice cold beer or Brinkelhoff. We have 7 diatomic molecules that we count as molecules. When we go to molecules and molecular compounds, the representative unit is going to be the molecule. And when it comes to ionic compounds, the representative particle is going to be the formula unit, the lowest whole number ratio of our positive and negative ions that make up that giant crystalline array. So we talked about gram atomic mass, gram molecular mass, and gram formula mass, and that equals the molar mass, the mass of a mole of atoms or molecules or formula units. And we just said, listen, we're going to just clump all these 3 terms into one giant term, the molar mass, the mass of a mole of whatever we're talking about. And so the molar mass is the gram weight of an Avogadro's number, whatever it is we're talking about. If we have a mole of two things, they both have the same number of representative particles. So a mole of sodium atoms gives me an Avogadro's number of them. That's equal to the same number of molecules, for example, in a mole of water. So all moles are the same, and so it gives us the same number of representative particles. Remember, this number 6.02 times 10 to the 23 is called Avogadro's number. All right, that is the end of part 1 of chapter 7. Thank you for your time.